Have you ever wondered how electricity actually gets to your phone charger? We all picture it like water flowing through a pipe, right? Millions of tiny electrons zipping through the copper wire to power our devices. Well, what if I told you that everything you learned in school about this is, at best, a useful simplification, and at worst, completely wrong? The real story is far weirder and a lot more amazing. The energy isn't flowing inside the wire at all. It's flowing in the space around it. Sounds crazy. I know. It blew my mind when I first learned about it. To understand this, we need to take a step back and look at what electricity really is. When you plug something in, you're completing a circuit. This circuit creates an electric field and a magnetic field. We learn about these in school, but we usually think of them as side effects. The real action, we're told, is the electrons moving in the wire. But here's the twist. Those fields are not side effects. They are the main event. The energy that powers your lamp or charges your laptop is carried by the electromagnetic field. Think of the wire not as a pipe for energy, but as a guide rail. The electrons moving inside the wire are incredibly important, but they move surprisingly slowly, like slower than a snail's pace. They create the conditions for the field, but they aren't carrying the energy themselves. The energy itself travels at nearly the speed of light, surfing on the electromagnetic waves in the space outside the wire. Let's visualize this. Imagine a simple circuit, a battery connected to a light bulb. You have two wires, one going from the positive terminal to the bulb, and one from the bulb back to the negative terminal. The battery sets up an electric field that points from the positive wire to the negative wire. At the same time, the moving electrons, the current, create a magnetic field that circles around each wire. Now, here's the key part. Discovered by a brilliant physicist named John Henry Poynting, he realized that wherever you have both an electric field and a magnetic field together, there's a flow of energy. He even came up with a way to calculate its direction and magnitude. It's called the Poynting Vector, and it's a fundamental concept in electromagnetism. When you apply Poynting's theory to our simple circuit, you get a startling result. The Poynting vector, the flow of energy, points from the battery through the empty space around the wires and then dives into the light bulb's filament. It doesn't travel down the core of the copper. The energy literally leaps out of the battery, fills the space around the circuit, and converges on the load, in this case, the bulb. The wire's job is just to guide this field to its destination. It's like the field is the train, and the wires are the tracks. The train isn't inside the tracks, it runs on top of them. This might feel counterintuitive because we can't see these fields. We see the wire, we feel it get warm, so we naturally assume that's where the action is. The heat in the wire is actually a form of energy loss. It happens because the electrons bump into the atoms of the wire material, creating resistance. This is like friction. So, the tiny bit of energy that does interact directly with the wire is mostly wasted as heat. The useful energy, the stuff that makes the light bulb glow, took the scenic route through the air. Let's consider an even more mind-bending example. Imagine a 1-meter cube of empty space. Now, imagine we have a powerful battery on one side and a huge resistor on the other, connected by two massive, perfectly conducting plates on the top and bottom. When we connect the circuit, a current flows through the plates, creating a magnetic field between them. The battery creates an electric field pointing from the positive plate to the negative plate. Now, where does the energy flow? According to Poynting's theory, the energy flows directly from the battery to the resistor straight through the empty space in the middle of the cube. It doesn't travel along the conducting plates at all. The energy is transported through the vacuum, guided by the fields established by the plates. The plates are just boundaries for the field. This is a very pure example that shows the energy transport happens through space itself. So why are we taught the water in a pipe model? Because for most practical purposes, like calculating voltage, current, and resistance in basic circuits, it works perfectly fine. It's a simple, effective model that lets engineers design and build all the amazing electronics we use every day. You don't need to be a theoretical physicist calculating Poynting vectors to wire a house. Ohm's law still holds true, but understanding the deeper reality is what pushes science forward. It's crucial for things like designing high-frequency circuits, antennas, and understanding how radio waves, microwaves, and light itself travel. All of these are forms of electromagnetic energy traveling through space. Your Wi-Fi router isn't sending electrons through the air to your phone. It's sending energy packaged in electromagnetic fields. The physics is exactly the same. The energy from the sun that warms the Earth travels 93 million miles through the vacuum of space. There are no wires connecting us to the sun. That energy is purely in the form of electromagnetic radiation. When that light hits a solar panel, it gets converted into electrical energy, which then flows, you guessed it, in the fields around the wires of the solar panel circuit. This concept even changes how we should think about a power grid. When you see those giant transmission towers, the massive amount of energy they're carrying isn't inside those thick aluminum cables. It's flowing in the vast space between and around them. The cables are just the guides for an enormous river of invisible energy, flowing through the air at nearly the speed of light to power our cities. The idea that energy flows in the fields was revolutionary. It unified electricity, magnetism, and light into a single theory of electromagnetism, one of the greatest achievements of 19th century physics, primarily thanks to James Clerk Maxwell. Poynting's work was a direct consequence of Maxwell's equations. So, the next time you flip a light switch, take a moment to appreciate the invisible wonder that's happening. The energy isn't just rushing down a copper tube. It's blooming out from the source, filling the space around the wires, and flowing through the room to its destination, guided by the very fabric of space-time. The world is so much more fascinating than the simple models we learn in school suggest. The wire is just a guide, but the real magic happens in the empty space all around it. Thanks so much for watching and expanding your mind with me today. If you enjoyed this journey into the weird world of physics, be sure to hit that like button and subscribe for more deep dives into the science that shapes our reality. Let me know in the comments what other physics myths you'd like to see busted. See you in the next one.